All right, everyone, welcome to another episode of the TWiML AI podcast. I am, of course, your host, Sam Charrington, and today I'm joined by Dan Friedman. Dan is a PhD student in the Princeton NLP group. Before we get into today's conversation, be sure to take a moment to head over to Apple Podcasts, Spotify, YouTube, or your listening of platform of choice. And if you don't already subscribe to the show, be sure to hit that subscribe button. Dan, welcome to the podcast.
Thank you. Thank you for having me.
I'm really looking forward to digging into our conversation. We'll be talking about your research that will be presented at this year's NeurIPS on the topic of interpretability for transformers, and you take a unique approach to that challenge. Before we get into that, though, I'd love to have you share a little bit about your background and how you came to work in the field of machine learning.
Sure. I'm currently a fourth-year PhD student in computer science at Princeton. I took maybe a roundabout path to machine learning. So my undergraduate degree was in English literature.
Oh, wow.
And yeah, I just took an introductory programming class, I don't know, junior or senior year, and I liked it a lot, and I kind of gradually pivoted.
That's awesome.
So I did a little bit of research as an undergraduate, kind of in NLP and sort of computational linguistics a little bit. Then I worked for a few years as just a software engineer. And then I decided to go back to graduate school to kind of see what was going on in the research world.
Awesome. Tell us a little bit about your research interests. What have you been studying over the past 4 years?
Yeah, what I'm mainly interested in now is the kind of general topic of interpretability. So I'm trying to better understand how these machine learning models that we have now can process natural language text.
Awesome. And are you specifically focused on transformers exclusively in your research, or are you kind of exploring the topic of interpretability broadly?
That's a good question. I think like the research landscape has changed a bit just in the last couple of years. So now kind of like transformer-based language models are just like sort of predominant architecture, not just in NLP. And so that's kind
Mm-hmm.
of what I've been focusing on more recently. Um, but I'm also, maybe more so in the past, have been interested in kind of like more sort of architecture agnostic approaches to interpretability, if that makes sense.
Mm-hmm. Sure. Some of the most popular approaches to interpretability, things like Lime, have been come out of that architecture agnostic approach. But I think what you are demonstrating in your the research that we'll be talking about is that if you uh, are aware of the architecture, and what's more, if you're able to manipulate the architecture, you can do a lot more with interpretability. Is that broadly the general idea you pursue with the research?
Yeah, I would say so. I think like another dimension of the point is just that the transformer has sort of proven to be incredibly effective architecture
Mm-hmm.
for sequence processing tasks, and so you can also think of it maybe as a way to sort of work backwards um, and say, could we take this model that works really well and try to like make it a little bit easier to understand the sort of rules that it's learning for all these tasks.
Mm-hmm. And now your research falls broadly under the category of mechanistic interpretability. Can you, share what that means and talk a little bit about some of the approaches that we've seen thus far in the vein of mechanistic interpretability for transformers in particular?
Yeah, this is a very good question because I don't know if mechanistic interpretability has such a precise definition, um,
Okay.
but I think in general the goal is to try to like take these neural networks that we train to solve a task and try to reverse engineer what the model is doing in terms of some more human understandable kind of algorithmic components. Um, right? So the models are operating in terms of uh, high dimensional representations. And the goal of mechanistic interpretability is to try to see if there's any kind of analogy between what the models are doing in kind of high dimensional space and some more familiar types of algorithms that we can think about and reason about as people.
The mechanistic distinction is versus, again, like Lime, I guess, or like observational or surrogate models, I guess is another approach. Like things that aren't like digging deep and trying to interpret what's actually happening in the model, but rather looking at, outputs or relationships between inputs and outputs and that kind of thing.
Yeah, I'd say one example of kind of a whole category of approaches in sort of earlier work on interpretability would be things like um, feature importance. So, say you have a
Mm-hmm.
sequence of texts and you have maybe a classifier, and their interpretability method will output, here are the words in your sentence that were important for making that prediction. Or
Mm-hmm.
kind of another kind of approach is finding examples in the training data that were influential for that particular prediction. And so these are kind of methods that can give you some hints about what the model is doing. They don't give you what I would call maybe like a sort of algorithm level understanding. So kind of one specific test is, you can't um, look at one of these, say, feature importance maps and then predict what the model will do on a new example. So I think maybe one goal or ambition of mechanistic interpretability is to give you kind of a representation of what the model is doing that you can sort of look at and simulate yourself.
Mm-hmm. Mm-hmm. And it strikes me that in addition to just solving the problem of providing some interpretability, this research is also aiming to take on another important task, which is to help us understand these models, which are increasingly important, doing amazing things, and we're not really always sure why or how they're working.
Yeah, yeah, 100%.
Yeah. So, in the paper, you talk a little bit about some of the prior work. There are approaches that look at attention heads. There are approaches that look at various network representations. Can you kind of characterize the prior approaches and their, I guess, shortfallings relative to the approach you're taking here? Which, of
Yeah,
course, we haven't gotten to yet, but we will.
yeah. So there's just a ton of prior work on interpretability, and I'm not going to do it justice, but
Yeah.
I would like give as a very kind of like simple summary. I kind of think of two categories of prior work. So one is sort of the sort of line of work, just sort of in the NLP world, on trying to understand models, like maybe beginning with BERT. So with the
Hmm.
BERT model, that kind of sparked a lot of interest into how is this model so good at all these NLP tasks. And so that work uses just a whole range of different kinds of methods for trying to like inspect different aspects of what the model is doing. So you have some of the methods I mentioned, like looking at feature importance or finding important training instances. And there's also some work on kind of peering into the internals of the model, like figuring out what information is encoded in the model's representations, or trying to understand the role of different attention heads. And I think, to me, what I see as like the main limitation of this body of work, and or first I should say that is all this work has revealed a lot of very interesting things about how these models are kind of working,
Hmm.
but it doesn't give us what I was kind of describing before as a sort of algorithm level understanding. So it doesn't give us a complete or faithful description of how the model is making decisions. And so it's not really a type of understanding that you can use to say, be confident that your model is always going to do what you intend. So, for example, you can't
Hmm.
verify your model in the same way that you would, you know, could verify software. Um,
Hmm.
so that's kind of one category of work. Then I think more recently, there's been a growing interest in this new approach, which comes under the title of mechanistic interpretability. I think maybe responding to some of those limitations of the existing work in interpretability. And with mechanistic interpretability, the goal is really to kind of reverse engineer an algorithm that you can sort of read and see, here's how the model is performing this task. It's represented as kind of neural network continuous computation, but actually we can sort of translate it to a format that's easier for us to understand. And so this is work that has largely been focusing on these large transformer language models, although there's also a lot of interesting work on small transformer language models. Um, and I think, again, yeah, mechanistic interpretability has also revealed a lot of interesting things about these models, but it's quite hard to do. So it requires a lot of manual effort. That sort of is maybe problem one. And I think maybe a more general problem is that you actually don't always, can't always be assured that there even is a kind of a human understandable description of what the model is doing, right?
Hmm.
So these models haven't been trained to be interpretable, and so they could be, processing information in all sorts of subtle and complicated ways. Yeah, our kind of motivations were, in part to try to have some kind of automated interpretability, and
Yeah.
also to maybe give us a way of specifying more of our own kind of preferences about what kind of like explanation do we want. So maybe uh, we can place more sort of bias the model to be more interpretable in some sense that we can specify.
Hmm. Hmm. And now the approach that you've taken, I forget if you use this term in the paper, but design for interpretability kind of comes to mind for me, and it kind of brings to mind like effort to design for manufacture in engineering and automotive engineering, for example, or engineering of goods, and or design for maintainability from a software perspective. It's like you've got this end goal. Uh, treat that end goal as central in a design process and come up with an approach that helps deliver it. What were some of the inspirations for you in taking this approach?
Yeah. So I'd say first there's been some prior work in machine learning kind of advocating for a similar goal of what is also sometimes called like inherently interpretable models or kind
Mm.
of intrinsically interpretable models. Um,
Hmm.
and a lot of that has come more in fields like computer vision, and for models operating on say tabular data and things like that. And so that's like kind of a motivation in general, but there hasn't been too much work in natural language processing. Then I'd say like a more immediate inspiration was a recent paper from Gail Weiss and collaborators called "Thinking Like Transformers." Um,
Hmm.
and so this is a paper that proposes a programming language called RASP, which you can use for writing programs in sort of a Python-like programming language that can be compiled into a transformer network.
Okay.
Um, so this is kind of a way of this was kind of proposed to as a way of making it easier to reason about the kinds of things that transformers can learn to do. So it's kind of a computational model for different types of information processing that this network architecture is capable of. But it also gives us this way of seeing the correspondence between the transformer and kind of a human readable uh, computer program.
How's this type of program different from PyTorch or TensorFlow program, which is also a Python program that
Yeah,
represents a transformer?
this is a great and sort of philosophical question. Um,
Okay.
I would say it's an alternative representation of what the model is doing. With the PyTorch program, I mean, okay, so one kind of like direct difference is the PyTorch program, you can't read that code and understand what the model is doing because you have to also look at the weights of the model to
Right.
understand the actual sort of solution.
It's not really doing anything until it's trained.
Right, exactly, and you can plug in different weights and get completely different
Hmm.
behaviors. So I think the analogy I'm thinking of is more like you take, say, a trained transformer. So you have
Hmm.
it's defined by the architecture, but really by the weights. Um,
Got it.
and can we kind of turn that into a sort of human readable program? So a human readable description of what those weights mean, if that makes sense.
All right. So you're inspired by this previous work, including RASP, and their Python representation of trained transformer models. And so tell us now about your approach and what you've done.
Yeah. Okay. So RASP kind of is this framework for um, writing down a program. So like you can write, say, a transformer program that will solve a particular task, say a program that will sort a list. And it's designed so that this program is equivalent to a particular instantiation of a transformer. So you can take the program and compile it into a set of weights um, for a transformer that will implement this program.
Mm-hmm.
But there's no way of training a transformer and decompiling it into a program. So this is what we want to do, right? So
Okay.
in RASP, you have to write all of the programs yourself, and then you can turn them into a transformer. But we'd like to
Mm-hmm.
just train a transformer. It can figure out, its own solution, and then convert it back into this alternate representation, sort of program representation that we contend is easier to interpret. So that's kind of the high level goal. And without getting into the weeds, basically what we do is we just design a set of constraints on the transformer weights that will guarantee that the corresponding model will always have a direct mapping to a sort of a RASP style program. So one way to think about it is that you know every RASP program corresponds to a transformer, but not every transformer corresponds to a RASP program. And so we
Mm-hmm.
want to kind of constrain our optimization to the subset of transformers that do correspond to programs. And so it's kind of a discrete optimization problem. So these are transformers that have discrete weights. They're kind of like constrained in various ways to keep things sort of clean and interpretable.
Mm-hmm.
And so we design a set of constraints, and then we kind of optimize this sort of discrete model using a kind of a continuous reparameterization. We use the Gumbel reparameterization to search in the space of discrete discrete models.
Okay. Okay. To get a little bit further into the weeds, the constraints seem to be the heart of how you're able to construct uh, this, essentially a space that only contains representable transformers. The first of those is you require disentangled residual streams. What does that mean?
Yeah. So this phrase is kind of inspired by some prior work in mechanistic interpretability, and this is sort of responding to a problem with if you just train a transformer from scratch, it's not necessarily going to be interpretable, in part because all sorts of information is jumbled up together in the representations. So every
Mm-hmm.
layer can calculate something, and the transformer has these residual connections. So each layer will add its output back to the input, from the previous layer. Um,
Mm-hmm.
and so actually, a lot of work in mechanistic interpretability is aimed at just solving exactly this problem. Like, how do you trace information through different components of the network, given that they're
Mm.
all kind of like over, writing to the same place?
Right.
It's sort of by analogy to a computer program, you can think of the residual stream, the model's representations, as kind of corresponding to memory in a symbolic program. And in an off-the-shelf transformer, all the variables are kind of being written on top of each other. Or you can think of like
Mm-hmm.
the same variable means different things depending on like the context. And so this first constraint is just to make sure that each kind of piece of information is stored at a dedicated address in the embedding space. Whenever a sublayer reads information from the residual stream, it's kind of constrained to only read a specific named variable from a dedicated address.
Mm-hmm. And is this constraint, how's it implemented? Is it like an objective function constraint, or is it a constraint between two training steps, or
It's a hard constraint. So
is it architectural in the sense of
yeah, well, maybe I can explain kind of more concretely. They're sort of like you can
yeah.
kind of divide this into two parts. So one is reading information from the residual stream. So reading a variable,
Mm-hmm.
and the other is writing a variable. So when we start out, at the first layer of the transformer, we only are storing two variables. So one is the token identity. So if one variable says what is the identity of the word at each position, and then we also have the a position encoding that tells us, what's my index in the position. So those
Mm-hmm.
are kind of two variables, tokens and positions. Maybe the writing part is easier to explain first. So we have each layer, say we have each attention head, and each feed forward layer will, calculate something based on the previous input, and then it will write some new information to the residual stream. And in a standard transformer, this is just done by addition, but we
Mm-hmm.
just replace addition with concatenation, basically. So, each
Okay.
attention head will get its own kind of new block in the embedding space. You can think of it as its own dedicated
Oh,
subspace in the representation space that's reserved exclusively for its use. So that's kind of, you could think of
got
it
it.
as an architectural modification.
Yeah. You implement the constraint by not doing the thing that the constraint that you don't want to happen, essentially.
Yeah, this is like realized in the in the code, right? So it's kind of
Right.
like, and you could realize this kind of constraint with a regular transformer, right? So instead of concatenating, you could just have pad all of your embeddings with zeros and add.
Mm-hmm.
But the model could learn to do this kind of thing itself, but we don't think it has much of a motivation to.
Got it. Got it.
So that's kind of writing to the residual stream. So we kind of keep all the information disentangled. And then
Mm-hmm.
we also want to make sure that each model is reading kind of a named variable. And so in a standard transformer, this sort of, you can think of reading information from the residual stream is sort of corresponds to taking some kind of linear projection of your embedding. So you have some learned weight matrix that will, you can think of it as reading off some information from some subspace of the residual stream. And we want to constrain the model so that this subspace corresponds exactly to one of these like named subspaces. So maybe we'll have some attention head that will read the token variable as one piece of information. Um, and so the way we implement the constraint is by, instead of kind of learning this whole a sort of a free ranging weight matrix, we just learn a gate over the available variables. So let's say you have two possible variables you can read in the first layer. We for each, say, attention head, for each piece of information it has to read, it will learn kind of, you can think of it as a distribution over two possible variables. And this is the sort of thing that we train. And then once it's kind of like picked a variable to read, you can kind of like project that back up to get the corresponding weight matrix in a regular transformer.
Talk me through the second constraint. You talk about modules in the paper. How
Yeah.
is that? What does that constraint represent?
So another way of describing that is that we have, you can think of our program as we have um, some number of variables, and we have
Mm-hmm.
some number of functions, and each function will read some variables that have been kind of written earlier in the program. It'll calculate something, and then write an output to a new variable. And
Mm-hmm.
so the second constraint is referring to that middle part of each module will have to calculate something. So we also want to make sure that each model is calculating something in a way that we can translate into kind of a interpretable sort of rule-based procedure. So we want to make sure that each sublayer itself is interpretable as well.
Awesome. And so you've got these constraints. How do you put those together to then generate the programs?
In a sense, we can kind of read the program off directly from the weights in this constraint model. So we kind of know what all the variables are, and we know what each module is reading. So let's say in our first layer, we can kind of look at the attention head, say. So an attention head, it's associated with three variables that it has to read. It has to read
Mm-hmm.
a key variable, a query variable, and a value variable. And so during training, it'll learn a distribution over the possible variables for each slot. And then after training, we can just sort of read it off. Say what does it pick as sort of the most likely variable, and we can say, okay, attention head 1 is reading the tokens variable as the key, and maybe the tokens variable as the query, and the position variable as the value, and so on. So that's the first kind of bit of information. And then we can look at each module itself. So we have our attention heads and feed forward layers, and the exact procedure depends on the component, but those also we can kind of read off a rule or a set of rules that are equivalent to the logic that that particular module is implementing.
Mm-hmm. And so the programs remain probabilistic because you're implementing that distribution or the distribution at these various layers in the programs?
No, so the program is not inherently probabilistic, although
Okay.
you could implement a probabilistic program within this framework in some sense. Yeah, to explain, we learn this distribution. The way I would summarize it is we are optimizing a distribution over discrete programs. And so
Okay.
we have all these gates, we have these distributions. So for example, for this attention head, we're trying to search for this distribution over which variable will attention head 1 read as the query variable. After training, we can just sample a discrete program from these distributions. Or what we do in our experiments is just take the sort of the argmax discrete weight associated with each distribution. So just take the
Got it.
most likely program. And so this is a discrete program that is not probabilistic.
Got it. So at the end of your process, you've kind of baked in all of the sampling, and there's ultimately a program that has a single output for a given input.
Yeah, I guess to give maybe one more detail, we do leave the final layer of the model is just a regular linear classifier. So those
Okay.
weights, that's the one kind of continuous part of the model. And the way I
Okay.
would think about it is we have the main kind of guts of the transformer is a feature extractor. And so it's a discrete feature extractor. And so every kind of sub path through this program is sort of answering a question about the input sequence. And so it's saying yes or no, here's some bit of information about the input sequence. And that's all discrete and that's all deterministic.
Mm-hmm.
But then you have a linear classifier that you can use in kind of the standard ways that you would use a linear classifier in machine learning. So you can have a kind of a stochastic decision rule, for example.
Okay. And what ensures that, well, let me ask the question first. By talking about reading the program from the model, I think was the terminology you used, is there a one-to-one mapping, meaning every representation has a single program, and presumably that falls directly from, is it just the disentangled residual streams that gives you that one-to-one mapping, or is it both of those constraints together give you that one-to-one mapping?
It's both of the constraints together. Yeah, so there's a one-to-one mapping.
Yeah.
There's some freedom in how exactly we express the mapping. So you can kind of write this sort of rule-based program in different ways. Um,
Mm-hmm.
but the rules, in a sense, are kind of like one-to-one.
Okay. And can you articulate like what the programs look like uh, without
Yeah.
visual aids?
Okay. So this is a challenge, but maybe I can. And there's a lot of examples in our paper, and we also have uploaded all of our learned programs to our GitHub repository, so you can download these
Mm-hmm.
programs and run them yourself. Um,
Mm-hmm.
and they're just Python programs. So I'd say the bulk of the program is in representing attention heads. So what does each attention head do? And so the attention head, the role of each attention head is defined by what variables is it reading. So what information does it read? So
Mm-hmm.
say what keys, what and queries does it read, and then what's its sort of internal logic for deciding what token to attend to given a particular query. And so I can give maybe the simplest example is if we're kind of starting at the first layer of the transformer. The only possible information we can look at is the token identity. So say what word is at each position, and also this position indicator. And so one
Mm-hmm.
common thing that the model learns to do is it will say, well, at each position, I just want to look at the previous position. I want to see what word appeared immediately before me in the sentence. And so in the program, that's realized by, first of all, we can see that this attention head is reading the position variable as the key and the query. So that's kind of part one. And then part two is each attention head will also be associated with a rule, which we call the predicate, which is tells you for every pair of key and query, should I attend to that? Or for every query, which key should I attend to? Um, so the way
Mm-hmm.
it looks like in the case of the position, the look at the previous token rule is you'll have sort of a sequence of if-else statements, and it will say if the query position is equal to 1, attend to the key at position 0, or attend to
Mm-hmm.
the token, the token that has a position equal to 0, and so on.
Yeah.
So that's kind of attention. And then we also have sort of a simple kind of feed forward layer, which is also it's a series of rules. So we kind of express the feed forward layers as just big lookup tables. So let's say we're trying to look for a particular bigram. So one example we have in the paper is for we train models to recognize whether all of the parentheses in a sequence are balanced. So if you have a sequence of balanced parentheses, is everything matched uh, nicely? And so one thing the model can learn to do is it can say, well, if I'm like an open bracket, if I'm an open, you know, parenthesis, and the next token is a closed square bracket, then this is an invalid sequence. Because if you open a parenthesis, you have to close it with a parenthesis before you can have a closed square bracket. And so that's the kind of thing that could be realized with the feed forward layer. So you'll have a feed forward layer, which will look at, what token am I looking at and what was the previous token, and just have a sort of a series of rules, a series of cases basically that say, output this value if I see open parenthesis followed by a square bracket.
How limiting is the constraint you oppose from a functional perspective? To what degree does it limit the um, the ability to represent uh, the types of transformers we might want to use? Is it does it enforce kind of an overly simplistic transformer that can't do the kind of that isn't practically useful, or do you retain the utility of transformers even with these constraints?
Yeah, that's a good question. Definitely the constraints we are simplifying, we are kind of restricting the set of transformers we can learn. So
Hmm.
we can't learn every kind of transformer. So one example that we can't have in our, models is non-uniform attention patterns. So in these models, it's essentially we have hard attention most of the time. So every query will attend to a single position, or
Hmm.
it will attend uniformly to a number of positions. We didn't really do any kind of formal analysis in the paper about how expressive is this subset of RASP that we're looking at, but I think some other work has found that even with these kind of constraints, the framework is still pretty expressive. And
Okay.
you could also trade off, you can get more expressive, you can sort of get closer to like the regular transformer by adding more layers, for example. So you can sort of approximate this kind of continuous transformer if you just have more attention heads and so on. I think the bigger challenge at this point is more about optimization. So
Hmm.
for the things we're looking at, we can kind of manually write a transformer program that's expressive enough to solve a whole range of tasks, but our kind of discrete optimization method doesn't always succeed in finding those nice solutions. So I guess what I'm saying is even with these limitations, this framework is quite expressive in ways that you can kind of work out or that follow from some prior work.
Hmm. And just so I understand the implications of the last thing you said, are you starting with a given transformer and finding a representation in this constrained space?
No, we're
Or I don't
searching.
remember you saying anything about starting from a. You're
No,
not
no, no,
trying to
no, no.
necessarily. Yeah. Okay.
Right. That's the whole thing. Yes, we're searching within this constraint space.
Right. Is there a connection between a particular set of functionality or transformer that you want to represent, or are you just kind of pulling, sampling from the constrained space that you've created and trying to find interesting things?
Oh, I wonder if I've made it sound more confusing than it is. We kind of define this distribution over discrete transformers. So we can kind of construct a probability distribution from which we can sample a set of discrete weights that
Hmm.
correspond to a model within this family satisfying these constraints.
Hmm.
And then we can optimize the parameters of that distribution using this um, Gumbel reparameterization. So
Hmm.
sort of resembles variational inference in some respects. So
Hmm.
this is we kind of can reparameterize these distributions so that they're differentiable, and then we can update, optimize the parameters of the distribution by sampling from these distributions and then using backpropagation to update the parameters of the distribution.
Right.
Um, so that's kind of the optimization that we're doing. So that's like the approach we take to searching within this discrete space.
And you're not searching for points in the space that meet the constraints because the space is defined by the constraints already, correct?
Yeah,
You're searching for what?
we're searching for the parameters of a probability distribution over programs. I think optimizing might be a more
No, this is fine, but ultimately you have this space defined by these constraints and you conduct a search and that search yields a program.
yeah. Well, so the result of optimization is this distribution over programs, and then we just take the most
You
likely
sample.
program.
Right.
We
Right.
sample
I
or
get
it's this factor distribution, so we can just take the argmax.
I get it. So I think where my question is coming from is so then you have this program that maps to a transformer. And I guess this is the point, right? You have a program that maps to a transformer. And so that is the interpretability that we're looking for because you've got this program that is a human readable program that you can inspect and understand what the transformer is doing. And I think what I was trying to connect to was I don't I don't want a random transformer. I want a specific transformer that does a specific thing. Can
Yeah,
I somehow apply this method to get a program out that maps to my transformer?
in a way, yes, and in a way, no. So first, I should clarify that the program it's trained to solve a particular task. So if you think of this sort of optimization procedure, we have this distribution of our programs, we sample one, we evaluate it on some batch of examples, and we see how good is this program at this set of examples. And then depending on the result, we can update our parameters to find a better program. So
So the search is task specific.
yes,
Yeah. Okay.
it's quite similar to training a transformer on a task, but it's training a
Yeah. You
transformer with
mentioned backprop.
yeah.
Correct. Okay.
However, you can't take a regular transformer. You can't download, GPT-3 and get a program out of it at this
Hmm.
at this stage.
And granted that you can't do that, are there like scale limitations or like inherent scale limitations to the approach? Talk a little bit about that.
Yeah. So I guess so. We maybe alluded to them some a little bit before. So one is maybe there's some limitation by the expressiveness of this framework. So maybe these simplifications mean that you can't do all the things that you can do with a regular transformer. Um, I
Hmm.
don't think that's like a major or like an insurmountable scale limitation. I think
Mm-hmm.
at the moment the more of the scale limitations come from some of the difficulties of the sort of discrete optimization. So in some cases we can manually write a transformer program. We can manually write a program that we know will like solve a task perfectly, but we find that our method doesn't always find these sort of good programs. I think that's because this sort of discrete optimization is difficult. And so I think the more immediate challenge to scaling this approach will involve trying to come up with some better approach to optimization that can alleviate some of these problems.
To close out, we alluded earlier to some philosophical thoughts you have on the various representations for a given transform, or if you have various representations, like how to think about that idea.
Yeah, yeah. No, I mean, another version of this question that comes up often is like, is code or is a computer program actually interpretable? And you
Mm-hmm.
actually know if you've read anyone else's code, often human written code is not interpretable at all, or it's very hard to understand. Um,
Mm-hmm.
and I think I would kind of think about this. I have maybe two responses. The first is that there is some sense in which this kind of discrete representation of a program or an algorithm is easier to interpret because we can do a lot of things that are very hard to do with the continuous transformer. So, for example, a lot of prior work in mechanistic interpretability has been devoted to this problem of circuit identification. So figuring out, finding kind of subgraphs of the model that form a coherent algorithm. With this
Mm-hmm.
program representation, that kind of problem is sort of trivially solved. The other point is that we also have access to a lot of tools for interpreting these models that are not available for your kind of continuous neural network. So, for example, you can take one of these programs and load it into a off-the-shelf Python debugger and set breakpoints and step through the program and use kind of existing tools for static analysis and so forth to inspect this model. But I think ultimately the probably the right way to think about it is to think about what are your goals in interpreting a model. So it could be different people will have different interpretability needs.
Awesome. Well, Dan, thanks so much for taking some time and sharing with us a bit about your research.
Thank you so much for having me.